I didn't know what setting I changed. That now I've got all big pictures of whoever's whatever. But that was a great yawn, Gracie.
Thank you.
All right, I sent you a email with a link, and maybe you saw it, maybe you didn't. Doesn't matter. You can find it now. Or I also put the file in the AP folder of Google Drive, so that works too. Or you don't even have to open it for now. You can just look on the screen. And follow along here. And open it later and work on it yourself or whatever. So, want to work on some graphing and some other mathematical equations for a few days, but for today, graphing, I borrowed this from another teacher. Graphing is an important procedure used by scientists to display the data that is collected during a controlled experiment. When a graph is put together incorrectly, it detracts the reader from understanding what you're trying to present. Most graphs have 5 major parts. Now, you can get a good thumbnail idea of the whole experiment or study that's being graphed if they did a good graph. See the 5 parts listed there: title, independent variable on the x-axis, dependent variable on the y-axis, scale, and legend or key. So the title depicts what the graph is about. The title should give the reader an understanding about the graph, and more than the graph, it should give them a good idea of what the experimenter's study is. A good title is closer to a sentence than a phrase. Titles in graphs are like super concise descriptions of the study and what the graph is showing. And it's usually on top. The top is not quite as important. So we've got our title, we've got our independent variable, which is controlled by the experimenter. Independent does not mean that it is not dependent on anything. It's dependent on what the experiment wants. Okay, I haven't seen this before. It might help you. The variable that I am testing, I for independent. I'm sure that's not why it's called independent, but that's a good way to remember. Common independent variables include time. By the way, time is always the independent variable. Generations, measurements, lengths, and distance. But the problem is sometimes these can be the other way around, except for time. Time is always independent. Time can never depend on anything else. I mean, at least in biology. I guess if we were in physics and we actually got to the place that we could approach the speed of light and mess with time, but yeah, somewhere in our children's lifetime, maybe. Okay, this variable, the independent, goes on the x-axis. It's always on the x-axis. If it's not on the x-axis, someone did something wrong. If you're making a graph for a AP question, it goes on the x-axis. If it's not, they will take points off, I'm sure. Okay, the dependent variable, the dependent depends on, they say, is affected by. I would say the dependent variable depends on the independent. What the experimenter measures. So we'll look at examples later on. but it is affected by the independent variable or dependent on the independent variable. It is actually the results. What you're measuring, I would say it's the results you're getting. Scale. Now, scale is tricky. When you did geometry, the scale was just, 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5. But in a scientific scale graph, you may have 1 to 5 minutes on your independent variable, and you may have 0 to 1,000 on your dependent variable. And if you just graph those straight out, you would have a graph that was like a column, very narrow and tall. And they usually kind of like the graphs to be more along the lines of the aspect ratio of a square or maybe a computer screen. So if you had your scale 1 to 5 on the x-axis, we would have like maybe, I don't know, 5.1, 5.2, 5.3, 5.4, 0.1, 0.2. And then on the y-axis, we might have 1,000, 2,000, 3,000, or whatever. So before you plot your data points, before you actually do your graph, you must figure out how much each box in your graph paper is worth. And it doesn't have to be 1-to-1. And also, it doesn't have to start at 0. I mean, if the data goes from 1,000 to 2,000, you don't need your graph to go from 0 to 2,000. If your data goes from 1,000 to 2,000, your graph only has to go from 1,000 to 2,000. But you should be consistent. Shouldn't be 1,001, 1,002, 1,003, 1,010, 1,020 on the same size boxes. And always make sure your scale is labeled with what it is and what the units are. So, 1,000 watts, 1,000 grams or microliters or whatever. Legend, which is not the same as legendary. I would claim to be legendary, but that would be just too disturbing to even be funny. Short description about the graph's data, most often used to show what different patterns or colors stand for on your graph. Like one data point might be dots, another data point might be triangles, another the control might be labeled with dots, and the first experimental variable might be labeled with triangles, and the second experimental variable might be labeled with squares. So you would have to say this is the control and this is the first experimental, and you would probably actually name what the first experimental was, but seeing as how this is such a generic example, we don't have a name. EXP, experimental. All right, so you can refer back to this part when we get to the practice. Some rules and tips. Always use a pencil to draw your graph, or use a computer graphing program. Those are pretty handy. They do have one big flaw. They used to, I guess they haven't fixed, but it's you may need a technical degree to even know how to use the fix. Always draw lines with a ruler, unless you have absolutely no choice whatsoever. Now, here's a big one. Use at least half your paper for the graph. You don't want a tiny little graph in the corner. Give yourself plenty of room. Make sure the independent variable is on the x-axis and the dependent on the y. Make sure you include all the parts that we described. If you are graphing multiple subjects, use different colored or pattern lines and explain them in the legend. Tell people what you're doing. And then choose an appropriate graph. Line graph usually measures a change in something over time. Bar graph compares individuals to each other with only one data point. And pie graph shows percentages. And if you have any questions along the way, you don't have to sit there quietly. You can talk, and you're going to be talking soon because I'm going to be asking you questions. So, following graph is a fair to good example. It has its problems. So, tell me some good things about this graph. What does it do right?
Both of the axes are labeled.
Okay. Not sure if that's how you spell the axes. Okay.
The title of it.
Okay, it is titled, but the title could be improved. How could the title be improved, Gracie?
It could give a time span, or it could.
Well, remember what they said? A title should be more of a sentence than a phrase.
Yeah.
Okay, so the title should be.
It could give like a location and make it more like a sentence.
More complete title, including possibly the things you said. That is correct. All right, somebody else was going to give a good on this one. Was it Josh?
Yeah. I said that it's neat and that you could tell what they're going for.
Okay. So it's clear and readable. Nicely laid out. They use their program, their Excel or their ruler or whatever. Okay, it's got what? We've got over here, we've got our legend. The X and Y axes are labeled. We already said that. People, notice, per 100,000. So they're giving us the scale. We don't really need a scale for a year because there's no other possible thing it could be. Anything else that could improve on this?
With the way that they're differentiating like each thing, like how they're shading for each date, like I guess they could be a little more precise with that because some of the shading looks the same.
Yeah.
Oh, I have one.
And to be fair, it's possible that on the original, before this was copied and copied and copied, it's possible it was better. What do you have?
Didn't it say that bar graphs are are they comparing the years, or is it like a progression over time?
It's comparing the years. So this is a single data point. How many people per thousand in a given year?
Okay.
So yes, you're right. If this was trying to show, actually this one, you're also right, could be done as a line, as a bar graph, because you are showing a progression over time, except for it's not a, I don't know how to say this. I have no clue. See how that line, wow, what was that? See how that line, when I drew the line, it dips up and down and all around, and it is not any kind of mathematical function. If you start to draw a line graph and you're getting this kind of a thing, it should probably be a bar graph, which this is a really, really pathetic bar graph. So just a kind of a rule of thumb, if it's not graphing as some kind of a curve, a smooth, steady curve, if it's graphing as a wave up and down and up and down, there's a good chance you should try it out as a bar graph. All right. The graph below is not a good graph. What's missing?
Labels.
Yes.
Title.
And I'm just going to point out to you right now that when I see kids do graphs, they often leave labels off. They put the numbers and they don't tell what's going on. And the labels with units. I mean, if it's not there, if the label isn't there, the units aren't there. But remember, you're supposed to put them. Title. Anything else?
A legend.
Yeah, we might say legend with only one line. The legend might have been described in the title, so maybe we wouldn't have needed, but because we don't have a label, we don't know if we needed a legend or not. Did they do the scale right? 20, 25, 30, 35, 40, 40. So those are all 5s, 10, 20, 30. Those are, whoa. Oh, what? If we had a label, we would probably understand what the 0.00 meant, but without the labels, we have no idea. Okay, experiment number 1, use the following data to create an appropriate graph and answer the questions. So what kind of graph do you think that data would take?
I'm gonna.
What did you say, Josh? Did Josh disappear? What kind of graph do we think this takes? I think you said something, Josh, but then you disappeared and we didn't really hear you.
A line graph.
Yes, this should take a line graph. We don't have fractions in a whole. We have 2 pieces of data and it is going over a range of time. So I don't have a ruler handy. I guess I should get a plastic ruler that I could lay on my screen without scuffing the screen. But let's answer some questions because there's our place to graph it. What is the dependent variable? Anyone? Just so you know, it's got to be one of those things.
The bubbles per minute.
All right, we've got 2 bubbles per minute, plant A and plant B, and they are dependent. Bubbles per minute. And why did you pick that answer?
Because it changes, and like for both of the experiments, and the depth is the same. Like they use the same depth to find how many bubbles per minute.
All right, the depth was the same for both experiments. That was a good hint. think about if you're the experimenter, which of those is easy to change directly? How deep you're measuring or how many bubbles there are? And how deep you're measuring is the one that would be easy for you to change. I suppose there might be, I can't even think how you would do different numbers of bubbles and see what depth they were coming from, but maybe you could figure out a way. So what's the independent variable then?
Depth.
Depth. And why did you pick that answer? Well, as you pointed out, it is the same for both of these, and that was a good hint, but that is what it looks like the experimenter would be manipulating. And we already said what type of graph would be best. It would be a line graph because we've got the series over time of two different things. Okay, what would the title be for this graph? Anyone?
Number of bubbles per minute per experiment based on depth
Okay,
in something.
bubbles produced by plants at a given depth, yes. Any other ideas? That's not a complete sentence, but we don't have a whole bunch of information here. Any other ideas? I think that one works. And by the way, it's probably bubbles of something, but we don't know because bubbles, come on, give me my pen back. So bubbles of whatever we don't know produced by plants. And we would probably tell what kind of plant if we actually had the information. So what kind of plant? Depending on depth. If we had more information, we could put it in there. It might be, if we had the information, it might be bubbles of oxygen produced by Elodea. That's just a kind of aquarium plant. When exposed to light at different depths or something like that, but we don't have that information. So what would you include in the legend of this graph? This, let's see, how about Mies? Are you there, Mies? What should go in the legend? I see your lips moving, but I don't hear any sound. Interesting. Speaker fails just when it's her turn.
Coincidence?
Anybody then? What should go in the legend? There's only two things because we have two
Oh, she's getting
data
on her
on
phone.
two different things. What?
She's getting on her phone.
Okay, we've got plant A and plant B. And our legend can be, let's call, whoops, B. Call B circles, A circles and B squares. What would you label the x-axis? Remember, the x-axis is the independent variable.
The depth.
Okay, depth.
Wait, I thought x-axis was the change. Oh wait, no, you're right. You're right.
Depth of plants. What?
I'm just dumb.
Yeah, okay, I'm not quite
Meter.
done. Depth of plants in meters. And the y-axis would be?
Bubbles.
Number of bubbles. Now, we're not going to put anything like meters or whatever, because number of bubbles is number of bubbles. There's not like meter bubbles or centimeter bubbles or inch bubbles. Bubbles are just bubbles. It's just the number of bubbles. So we can add these things now. And we have to decide what our scale is going to be. So our depth goes from 2 to 30. It would probably be convenient to call that 0 to 30. And our lowest number of bubbles is 10. And our greatest number of bubbles is 50. So this scale is going to need to go from 10 to 50. If you're not following what I'm saying, you should ask. Now, we could go 0 to 50 if we wanted. So 10 to 50 on the bubbles. And you're probably going to have to remind me of those because I'm going to get it out of sight. 0 to 30 on the meters and 10 to 50 on the bubbles. So we say right here that on the y-axis, we need number, not hashtag, of bubbles. And on the y-axis, we need depth in meters. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 4, 5, 6, 7, 8, 9, 30. So we've got 30 squares. What were we going?
0 to 30.
Oh, well, that works very conveniently. We'll go 1 to 30. And then we'll come out just like that, because actually our first one was at 2, it wasn't at 1, so hopefully I counted right and didn't miss any. So we've got 10 to 50. I'm just going to guess there should be 50 squares there. So we can go, I better count. I'm not going to count if we're off. I'm going to go 0 to 50. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Look at that. I end up counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Maybe there aren't 50. Maybe it's a good thing. There are not 50. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, it looks like we're going to have to go by 2s to make this all fit. So 2, 4, 6, 8, 10 is right here. 2, 4, 6, 8, 10 is 20. 2, 4, 6, 8, 10 is 30. 2, 4, 6, 8, 10 is 40. And 2, 4, 6, 8, 10 is 50. Now, I think some students look at this and are like, oh, I didn't use all the graphs they gave me. That's not really a problem. Now, if we only used this much of the graph they gave us, that would be a problem. But we're doing a pretty good job of filling this up, so I don't think we need to worry about it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good, I didn't, oops, 20, not 10. All right, so do any of you have this open, or are you just looking at my screen?
I mean, I've been flipping back and forth.
All right, well, so if you've got this document open, I want you to tell me the data so I can mark it down and not have to keep scrolling up and down. So in the first column, our first number is 2 for depth. Is that correct?
Yes.
All right, so there's 2. And what's our second number for depth?
29. Or no. Nope. Sorry, that's 5. 5.
2, 3, 4, 5 is right here. And the next number?
10.
So that's right there. Next.
16.
16, 11,
Yep.
12, 13, 14, 15, 16.
25.
21, 22, 23, 24, 25.
And 30.
Okay, so right there. All right, what did we say plant A would be? Plant A is circles. So what's the 2 number for plant A?
29.
So 2 and, all right, what's the 5 number for plant A?
36.
30. Wait a minute, I did not quite do that right because we're counting by 2s. So 29 should actually be in the middle of that box. And then you said 36, 2, 4, 6. And what's the number for 10?
45.
2, 4, 6. So 10 would be right in the middle here. And the number for 16?
32.
Oh, we've got what I told you we didn't want, don't we? 32. And then for 25 next?
It's 20.
Okay. 25 is 20?
Yep.
Right there. And 30 is?
10.
Now, we do have what we want. Here's the deal. You look at this and you are very likely to say that the line should go like this. The line should not go like that. It didn't tell you in the instructions, but you may remember from biology, and I think I mentioned it in physics, that we want best fit lines. It turns out that bubbles is not a highly technical, highly refined measurement, and these are probably not, have some margin of error. So the line should be a best fit line that would look something like that. Some are above, some are below, and it kind of averages out like so. Now so we can see it better, I'm gonna go to squares and change color. So let's see, for the second plant, what's the number for 2?
21.
So 21 would be in the middle of that line. 5,
27.
2, 4, 6, 7. 10.
40.
Wow. 16.
50.
Need to see everything. So 16 is
That orange dot. And go up to 50.
25.
34.
Okay, 25. 30, 2, 4 would be right there. And 30.
20.
All right, best fit. What do you think on best fit for this? Just guess. What do they say? Fit wad. Just shoot things out what you think it might be.
Like a straight line in between 30 and 40.
I can see how you would say that, except for it doesn't look like a linear function to me.
Would it be like going just straight up because that hits 4 of them instead of like 3?
Well,
Like straight, like
that is a logical answer, but it still doesn't look like a linear function to me. In other words, this doesn't have to be a straight line. I think our line on this one would probably look something like this. And actually, the way those points are laid out, it does pretty much hit the points. Maybe this one's a little bit below. Maybe this one was, maybe I should have been a little below this. I mean, maybe that's not exactly what it should look like. But just because one line's a straight line didn't mean the other one had to be a straight line. But what we do not typically see in nature is something that looks like, wow, 2 cars going down the road at the same time.
in Dansville?
In the country outside of Dansville on a stay-at-home order. My goodness.
Whoa.
What we almost never see in nature is that kind of a function, especially with something as simple as depth. So how would you know that? I don't know a good way to know it. If it looks like a line is the best fit, draw a line, straight line. If it looks like a curve is the best fit, draw a curve. We're likely to see things like this, straight line. We're likely to see we're likely to see straight line functions. We're likely to see up and down or down and up. We're likely to see increases that curve one way or the other, or come up and level off, but we are not likely to see up and down and up and down and up and down. That is not something that happens very often or at all, if at all, in nature. All right, any questions? I want you to do the graph for experiment 2 for tomorrow. I'd like you to take a picture so we can look at your pictures. And we will continue with this tomorrow. So unless you have any questions right now, that'll be it for today. Anything? All right then, Bible class in 10 minutes-ish. Have a good 10 minutes and we'll see you in Bible class.
Good night.